This video will start the lessons for Chapter 10, which deals with trigonometric functions. Now, as you know, we covered some of the trig ratios in the previous videos in the previous chapter. This is going to expand on that topic to work beyond just working with triangles and to look at these as actual functions. The things that we are going to cover in this section talk about, given an angle, we want to be able to find the coterminal and the reference angles. We want to be able to find trig functions of any angle in standard position. And we want to find an angle given a trig function. So again, we're going to be using those inverse trig functions. Now, section 10.1 starts off with a few definitions. The first thing is we need to talk about what it means for an angle to be in standard position. And if you remember, any angle has an initial side, the starting side, and a terminal side. So for an angle to be in standard position, the angle's initial side lies on the positive x-axis. In other words, we're always going to be starting with the horizontal, and we're either going to be measuring up or measuring down from this position. So if we are measuring up, if we are measuring counterclockwise, then we have a positive angle. If we measure down or clockwise, we have a negative angle. If we talk about our axis here, we can talk about going around this axis as many times as we want and still ending up at the same point. And so technically there's an infinite number of angles which are considered to be coterminal. So this is two angles that share a common terminal side. And again, these have to be angles that are in standard position, so they have the same starting side and the same ending side, but essentially either we went all the way around or we could have gone from the axis and gone around this way to get to it from the negative direction. Either of those would result in coterminal. Either that pink or that green angle would be coterminal to the blue one. The other thing to talk about real quickly is what it means to have a quadrantal angle. And a quadrantal angle is one in which an angle in standard position whose terminal side lies on one of the axes. So if we think about this, we can either have a 90-degree angle if we go over to the positive y-axis. We can have a 180-degree angle. If we go over to the negative x-axis, we can have a 270-degree angle if we go around to the negative y-axis. Or we can talk about those coterminal angles. What happens if we go around in the negative direction? Well, if we go around from the negative direction to 90, we end up with negative 270 degrees. If we go around to the negative x-axis here, we end up with a negative 180 degrees. And if we look at this last one, we end up with a negative 90-degree angle. And again, these are not the same angle, but they are coterminal angles, which will produce the same trig ratios when plugged into those functions. Let's take a second and look at actually drawing an angle in standard position. So we want to draw the graph of an angle in standard position whose terminal side passes through the point -1, 2. So all we're going to do here is first we're going to label our graph so we know what each unit stands for. And then we are going to go back 1 because -1 and up 2, and that's our point. and we draw a straight line up to this point, and then we draw the angle over and we label it as theta. So this would be an angle in standard position, and we'll talk about here in a second how we can find those trig functions for any angle in standard position. So we've already talked about the trig functions, and if you remember, sine of, we'll call this theta, is going to be your opposite over your hypotenuse. Cosine of theta is going to be the adjacent side over the hypotenuse, and tangent of theta is going to be the opposite side over the adjacent side. Now, if we look at a triangle that's put on the x-axis, we can always talk about its dimensions as being x by y. So in this case, our opposite side, if we label it this way, is going to be y over hypotenuse, which we are going to call r, or the radius. For cosine, this is going to be the adjacent side, which is the x value, and the hypotenuse again is r. And finally, the tangent is opposite over adjacent, so y over x. And so these are the trig functions with regards to xy coordinates. Now let's see if we can do a few examples with this. We want to find the values of the trig functions for an angle theta in standard position with a point 27. So the first thing we want to do is we want to draw our angle. So we'll draw our grid. And again, we'll label our axes. In this case, we went out 2 and up 7, so it's a rather steep angle. And if we were to draw this back down to make the triangle, we would come down here at 2. And again, our height here is at 7. So the first thing we need to do is we need to find r, or the hypotenuse. So that's the same thing as before, Pythagorean theorem. R is going to be the square root of 2 squared plus 7 squared. So we end up with the square root of 4 plus 49, which is the square root of 53. So we're just going to leave it as the square root of 53. And we don't need to find a decimal approximation for that. So if we want to find the sine of theta, well, we said the sine of theta is y over r. If we think about it, the opposite side, 7, over the r we just found, square root of 53. And again, we don't like to leave radicals in the denominator, so we are going to rationalize it by multiplying by the square root of 53 over the square root of 53. Again, we're just multiplying by a fraction of 1 here. And we end up with sine theta being 7 root 53 divided by 53. Now, if we look at cosine theta is going to be the adjacent side, 2, or x, over the radius we found was the square root of 53. Again, we need to rationalize that denominator. And we end up with cosine theta being equal to 2 root 53 over 53. And finally, tangent of theta is going to be the opposite, or the y, which is 7 over the adjacent, or x, which is 2. And we don't have to do any rationalization for that because we have whole numbers. So take a second, make sure all of this makes sense before we move on to the next example. Now in this next example, we want to find the trig functions for the point 35. Again, we are going to draw our axes. So we have our point 35. Again, we're just plotting this like we normally do. We're going to draw our line up, and then we can drop our vertical to get our 90-degree angle. And theta is always going to be over here by the origin. Real quick note, the angle is always going to be between the x-axis and the line that we create. So in this case, again, we need to make sure that we find the radius. So r is equal to the square root of 3 squared plus 5 squared. And this is equal to the square root of 9 plus 25, which is the square root of 34. And again, we're not going to worry about simplifying that. So in this case, sine of theta, again, is going to be your y value. So 5 over your r you just found is the square root of 34. Again, we need to rationalize that, so we're going to multiply by the square root of 34 over the square root of 34. And we are left with the sine of theta is 5 root 34 divided by 34. Now, cosine of theta is going to be equal to our x value, 3 over the square root of 34. Again, we rationalize by multiplying by the square root of 34 over the square root of 34, and we end up with cosine of theta is 3 times the square root of 34 over 34. And finally, we have the tangent of theta, which is just going to be the y value of 5 over the x value of 3. So at this point, I want you to pause the video and try example 4. So in this case, again, if we draw our graph and find the radius, we should have found it to be the square root of 136, which does simplify to be 2 root 34. And we want to make sure that we reduce this so we can reduce fractions later, because as you see when we get to sine of theta, we have 10 over 2 root 34. Again, we rationalize and simplify, and we end up with 5 root 34 over 34, which is the same thing we had up here. Cosine of theta is, again, 6 over 2 root 34, which reduces to be 3 root 34 over 34. And again, that ends up being the same thing we had up here. And the tangent of theta ends up being 5/3, which is the same that we had up above. And if you remember, we talked about similar triangles in the last chapter, and these two triangles are similar. If you multiply the x value by 2 and the y value by 2 and the radius by 2, we end up with the second triangle that's in example 4. Now, one thing that I want to make sure that everybody is very aware of is that we always need to make sure that we include the theta anytime we deal with trig functions. We cannot leave this out. Again, we need to have something that the function is operating on. You wouldn't just write a plus sign and expect people to know what you are adding together. You wouldn't just write a square root symbol with nothing underneath it, because then it wouldn't mean anything. It would just be a function. It wouldn't actually be acting on anything. So in this case, we always need to make sure it is very important that we put theta down every time. Also, so that we know which angle we're talking about, that we're talking about this angle down here, theta, and not this one up here, phi. So we need to be very specific and make sure that we include that information. The last thing I want to talk about in this video are the reciprocal trig identities, and we've already talked about these in the previous sections. Again, cosecant is the reciprocal of sine, so this would be 1 over the sine of theta. Again, make sure that theta comes with sine, and therefore sine is the reciprocal of cosecant, so we could write that as such. Cosine and secant are reciprocals, so secant is 1 over cosine of theta, cosine is 1 over secant of theta, and finally tangent and cotangent are reciprocals, so tangent is 1 over cotangent of theta, and cotangent is 1 over tangent of theta. So if we went up to the previous example and we wanted to find the reciprocals here, we would probably actually go with the unsimplified version. In this case, cosecant of theta for the above example would be 2 root 34 over 10, because this time we don't have to rationalize, we just have to simplify. The 2 divided by 10 leaves you with a 1/5, and this becomes the square root of 34 over 5, which does look different than the sine theta if it had been flipped over, because we would have had to rationalize again and then simplify, and it would have been a little more complicated. For secant of theta, again, we look at the original one that we had written down for cosine, which was 2 root 34 over 6. Again, we simplify that, we get 1/3. And this becomes the square root of 34 over 3. And finally, cotangent of theta, if we flip tangent over, we can use either one of those. 3/5 is what we end up with for cotangent on that problem. So this concludes the first video for section 10.1. The next video will talk about angles that are not in that first quadrant.